Lesson 3.4, Day 1, Solving Exponential Equations. The learning targets for this lesson are that you will be able to solve exponential equations with two exponential expressions of the same base, be able to solve exponential equations with only one exponential expression, be able to solve exponential equations with two exponential expressions of different bases, and that's the tough one, and the toughest one, solve exponential equations in quadratic form. For all answers, we're going to round to the nearest hundredth. Normally we'd round to the nearest 10,000th place, but they're giving us direction here, which is 4 decimals out. To round to the nearest hundredth, so 2 decimals out. To undo an exponential function, you've known this since lesson 3.1, use a logarithm of the same base. Or if the bases are the same, the exponents must be, for example, look at this problem down here. 5 to this power, 5 to that power. I don't know what the power is, but for this equation to be balanced, these exponents have to be equal. So if I have two bases, if I can somehow get them to be written in the same way, then I can solve like this. All right, solving an exponential equation using inverses. This one, we only have one base and one exponent, so we have to get the exponential expression by itself. To do this, I'm going to add 5 to both sides first. 4 to the power of x equals 22. To undo, I only have one exponential expression on this side, so we're hitting this second learning target right there. To undo this, I'm going to use a logarithm of the same base on both sides. Log base 4 of the left side equals log base 4 of the right. Whatever I do to the left, I have to do to the right. Well, using the inverse property, this is just x, and this is exactly equivalent to log base 4 of 22, which if I use the calculator, log base 4, and I don't have it in here, so I'm going to change the base. Log of 22 divided by log of 4 gives me 2.23. I could have also used the option under math. Nope, not under math. Under math, yes, not number, under math. Log base 4 of 22, and it also would have given me 22.22. We have another problem like this. It's this problem right here, letter B. It only has one base on one side, so we need to isolate that base. If there was anything multiplied by it or added outside of the exponent, like down here, we would need to get rid of that first. Since we've got the base and exponent isolated, we're going to undo the exponential function. The base is e, so we're going to use natural log on both sides. So this will be the natural log of e to the 4 minus 3x equals the natural log of 6. On our left-hand side, using the inverse property, we now have 4 minus 3x equals the natural log of 6. To solve for x to the natural log of 6, we're going to subtract 4 or from it. The opposite of 3x equals the natural log of 6 minus 4. The natural log is only on the 6. And now we'll divide every term by negative 3. Or do the difference of those two and then divide by negative 3. So x is equal to exactly the natural log of 6 minus 4 all over negative 3, which, if I put in my calculator, the natural log of 6, close parentheses, minus 4, and then divided by negative 3, I get 0.736, which rounds to 0.74. On the next two problems, we see that they have the same base, solving exponential equations with the same base. That is this learning target, the very first learning target. If they have the same base and no other operations on either side, the left or the right, then their exponents must be equal. So 3x minus 2 equals 9x plus 7, and we can solve from there. Here, they both have a base of 1/3, so their exponents of 5x minus 1 and 2x minus 3 have to be equal in order for this expression to equal this expression. When we solve here, we have 6x equals -9. Divide by 6, x equals -3/2. We should plug it back in to both sides to make sure that it works, putting this on the left-hand side of our calculator, this on the right-hand side, making sure when we plug in -3/2, the equation is balanced. Over here, we do the same thing. I'm going to subtract 2x from both sides and add 1. When I divide by 3, I get x equals -2/3. I will again plug this equation, this expression in for y sub 1, this expression in for y sub 2, plugging in -2/3 for x, verifying that those are actually balanced when x equals -2/3. Solving exponential equations with similar bases. When I say similar bases, I mean bases that we can force to be the same because they could have the same base if we manipulate them or change them slightly. So in letter A, I've got exponential expressions, and I don't want to use a logarithm unless I have to. I could, but it'll get a little more complicated. So I do that if I can identify that this is really 6 to a power. 36 is really 6 squared, and right now it's being raised to the x plus 1. I'm supposed to, when I have an exponent on top of an exponent, multiply those exponents. So this is really 6 to the 2x plus 2, because we would have to distribute the 2 to both the x and the 1. On the right-hand side, it already has a base of 6. So now, I just set the exponents equal. 2x plus 2 equals x plus 6. Get our variable to one side and subtract 2 from both sides. I get x equals 4. Once again, I should double check that 36 to the 5th power is the same as 6 to the 10th power. And they are, so we know we did it correctly. Letter B. They don't look like the same base, but this is 2 squared and this is 3 squared. So if I look at this as 2/3 squared raised to the power of 3x over 4, now all I need to do is multiply the exponents. Remember, this is 2 over 1 and this is 3x over 4. So the 2 does not get multiplied by the denominator, but rather the numerator, giving me 6x over 4 as the exponent when the base is 2/3. Now that I have the same base, in order for this equation to be balanced, the exponents must be equal. So x minus 5 will have to equal 6x over 4. Since the least common denominator is 4, I will multiply every term by 4, leaving me with 4x minus 20 equals 6x. I will subtract 4x from both sides, leaving me -20 equals 2x, dividing by 2, x equals -10. I will verify this in the calculator. 2/3 to the power of -10 minus 5 gives me this decimal approximation. And 4/9 raised to the power of 3 by -10 divided by 4 is the same decimal value. So we know we have the correct answer. All right, looking at letter C, I only see one base here. But because they're telling me that I'm supposed to treat it with it as being as similar bases, I know that 64 is really 2 to a power. 2 to, I believe, the 6th, but it might be the 5th. It is 2 to the 6th. I was correct. So since that's 2 to the 6th, I now have 1/2 of x equals 2 to the 6th. They're still not written in terms of the same base. I don't like that this one's written as a fraction, so I'm going to change this one, but you could have done the same thing. You could have made this a fraction, changing this one. So this is really 2 to the -1st power, that's what 1/2 is, raised to the power of x. So it's really 2 to the opposite of x, when I multiply those exponents, equals 2 to the 6th. Now that they have the same base, the exponents have to be equal. Since the opposite of x equals 6, x must be the opposite of 6. And I could put that back in here. 1/2 to the -6 power. Flip it, it would be 2 to the 6th is 64. D is a little easier to decipher because this base and this base are both multiples, well actually not just multiples, but can be found using a base of 3. This is 3 squared raised to the power of x minus 3. This is 3 cubed raised to the power of 2x plus 2. We will need to be careful to make sure to distribute this exponent to every term of the other exponent, giving us 3 to the 2x minus 6. On this one, giving us 3 to the 6x plus 6. Now that we've established the same base on both sides of the equation, we can set the the exponents equal. Get our variable to one side by subtracting 2x, subtract 6 from both sides, and divide by 4, we get x equals negative 3. When I plug it back into the original equation, 9 to the negative 3 minus 3 is to the negative 6th. 27 to the 2 times negative 3 is negative 6 plus 2. We get the exact same decimal equivalent. That concludes learning target 3, solving exponential equations with two exponential expressions of different bases. Where we are trying, no it doesn't, that's where we're trying to force them to have the same base. So it's a little bit like number 1, but it's slightly different. This next part is where they have completely different bases. They don't have similar bases where we were able to force them to have the same base. But 4 and 3, 4 I could write as 2 squared. 3 is just 3 to the first. They will not ever have the same base. When that comes, we need to be very careful how we solve. We're going to use a common logarithm on both sides. Some people prefer to use log base 10, some people prefer to use log base 3 or log base or natural log. All of these can work. Your textbook usually uses natural log, so that's what I will do in this video, but if you'd like to try another one, you can show me in class and make sure that you're doing it correctly. So because I can't undo this exponential equation, I'm taking the natural log of both sides. But notice that I'm moving the exponent to the top, because when I do this, I'm actually going to try to expand this a little bit by moving that exponent in front. I have 3x minus 1 times the natural log of 4 on the left-hand side. Moving this exponent to the front, I have 2 minus x times the natural log of 3 on the right-hand side. Now I will distribute the natural log of 4. So I have 3 times the natural log of 4 times x minus the natural log of 4. On the right-hand side, when I distribute natural log of 3, I have 2 times the natural log of 3 minus the natural log of 3 times x. You may want to put those in parentheses so you don't confuse that x is not inside of the logarithm. The logarithm is part of the coefficient on x. X is not inside the logarithm, it's part of the coefficient on x. Be very careful of that. Well, now we're trying to solve for x, so our goal is to get these two terms to the same side. If we can get those two terms to the same side and everything else to the other, then we'll be in a good place. So I'm going to add this to the other side. I have 3 natural log of 4 times x plus the natural log of 3 times x equal to, so I added this to the left side. Now I'm going to add natural log of 4 to both sides to move it to the other side. So I have 2 natural log of 3 plus the natural log of 4. Our goal is to get x by itself. Right now I have 2 terms with x. I cannot, well I actually could combine them since they're both natural log. I could also factor out x, but I could combine these. This is 4 cubed and this is natural log of 3, so I could do 4 cubes times 3. I'd have the natural log of, what is 4 cubed? 4 cubed times 3 would be 192. It would be the natural log of 192 times x. I could also just factor out x. X is a common factor of these two terms being 3 natural log of 4 plus natural log of 3. On the other side, I have 2 natural log of 3 plus natural log of 4. And so, to solve for x, I will divide both sides by this expression. 3 natural log of 4 plus natural log of 3. At this point, you can decide whether or not you want to condense these expressions, since they have the same logarithm, and divide, or, since we are going to have our calculator available to us, do 2 natural log of 3 plus, well, we'd put it in a parentheses for the full numerator, 2 natural log of 3 plus natural log of 4, close parentheses for our numerator, parentheses for our denominator, 3 natural log of 4 plus the natural log of 3, close parentheses for our denominator, and get our answer at roughly 0.68. If we wanted to make sure, then this would be 3 squared natural log of 9 plus natural log of 4, which would be the natural log of 36 over, we'd have 4 cubed, which is 64, times 3 would be the natural log of 192, which in division could be the natural log of 36 minus 192, which would be a problem. You can't do the natural log of a negative 156, so I made a mistake somewhere. So I would just leave it like this, divide those two, and it should work. All right, let's take a look at letter B. We can come back to that if you have questions on that one tomorrow. Again, because we'll never be able to achieve the same base, we're going to use natural log of both sides. All right, so we're going to grab a sheet of paper so it's not as messy in there. I have the natural log of 6, and I'm going to bring that exponent in front, 2x plus 4. And on the front of this, I have the natural log of 5 to that exponent, but I'm going to bring that exponent in front, opposite of x plus 1. So I did the natural log of both sides, but then because I'd have an exponent on it, I moved it to the front to expand it. So when I distribute this, I have 2x natural log of 6 plus 4 natural log of 6 equals negative opposite of x natural log of 5 plus 1 times the natural log of 5. Might be easier to do it this way with the x before the natural log so that you don't accidentally put it inside the log. All right, now I need to get the x's to one side, so I'm going to add this one. So I'm going to add x natural log of 5, and I'm going to move this one by subtracting it away, minus 4 natural log of 6. So on the right-hand side, I have natural log of 5 minus 4 natural log of 6. On the left-hand side, I have 2x natural log of 6 plus x natural log of 5. If you look carefully, you can see that we have an x in both of these and a plus sign. So I'm going to factor out the x, leaving me with 2 natural log of 6 plus natural log of 5 equals, on this side, natural log of 5 minus 4 natural log of 6. To get x by itself, I will divide by that entire quantity. 2 natural log of 6 plus natural log of 5. And I either have to be careful how I do my parentheses, or I can combine these. This is 6 to the negative 4th. That's going to be complicated, so I'm just going to leave it like this. Natural log of 5 minus 4 natural log of 6 divided by, in parentheses, 2 natural log of 6 plus natural log of 5, close parentheses for the denominator. So that's exactly how I'm going to type it in the calculator. Parentheses, natural log of 5 minus 4 natural log of 6, close parentheses, divided by parentheses 2 natural log of 6 plus natural log of 5, close parentheses for the denominator, hit enter, and we get approximately negative 2.82 when we round to the nearest hundredth. This concludes the example for solving when the bases are two different bases.